with Krzysztof MEISSNER of University of Warsaw. You will talk about the conformal anomaly in gravitational waves.
Thank you very much. It's a great pleasure to be here for the workshop. I would like to show some results, recent results. The talk is based on 3 papers. This one appeared today in the morning in the archive, so it's very, very fresh. I would like to emphasize the role of conformal anomaly in deciding whether a given theory is admissible or not, the extension of the standard model. And I would like to argue that with the non-vanishing conformal anomaly, the gravity theory, as we see it, would be completely different. So, in fact, the fact that we have planetary motions, gravitational waves, and so on, is the proof, quote unquote, that gravitational anomaly vanishes. So let's start with chiral anomalies because they are well known. That's the definition of some effective action by the integration of some field coupled to a gauge field. Then the anomaly is the difference between W of A prime minus W of A if S is invariant under the gauge, the gauge in the form notation. And we know that in d dimensions, where d is 2n minus 2, there is a Chern-Simons form defined in this way, and the anomaly is given by the difference of 2 Chern-Simons forms, but in one dimensional, on the manifold one dimension higher, and in d dimensions it cannot be written as a difference of 2 local expressions. So that's the chiral anomaly. As we all know, its standard model has all local anomalies vanishing. It's an amazing fact that is sometimes not very much emphasized, that, for example, we have several kinds of anomalies because of this fact that this has 3 A's in it for n equals to 3. We have to triangle. In n dimensions, for example, we would have a hexagon to calculate the anomaly. In 4 dimensions, we have a triangle because the number of A fields is 3. And then, therefore, we have possible forms with 3 gauge fields. So we have hypercharge U1 to the third, sum of all yk to the third, sum of all hypercharges to the third power is 0 in the standard model. That's another possible anomaly. Sum of the doublets up into SU2 should be 0, where the plus sign is for left chiral fields and the minus sign is for right chiral fields. We have possible SU3, sum over quarks should vanish. We have SU3 to the third, because we know there is a totally symmetric gauge invariant with 3 trace of TA, TB, TC is DATC for SU3. It is not there for SU2, but there is equal number of left and right quarks in the standard model, so it vanishes as well. There is also gravitational anomaly with U1 Y, where sum over all should be 0. So we have several equations in the standard model. Right chiral neutrinos, that now we know that they are there in the standard model because neutrinos are massive, so there must be right chiral neutrinos. They do not have any quantum numbers of the standard model, so they do not contribute to any of these equations. So what is important, there is also in the standard model, there is a lepton number current and the baryon number current. They are separately, they are anomalous, but their difference is not. It's a very peculiar fact. Some people say that it points to the fact that B minus I should be gauged, but it's not necessary, but it's a very important fact, and I will use it at some point in the lecture. So, solving all those has the unique solution, and this is a very, very fundamental fact about the standard model. In fact, something that is absolutely crucial to our existence, that the electron charge is minus the proton charge, comes from solving these equations. Yeah.
What is it you want by gravitational anomaly here?
That's R squared, twice R squared. So U1 trace R squared is because there is not thrice L to the third, there is no pure gravitational anomaly in 4 dimensions, because it has to be even number of R's. Okay, so this fact, which was rather accidental in the original formulation, because of solving these equations, is a necessity for Islamic law, so it's very important. Okay, so now conformal anomaly. Conformal anomaly is related to the one-loop divergence. If we calculate the one-loop divergence, let's think now about the conformally invariant theory. Then the divergence is in the form of L to the fourth plus L squared plus logarithm L squared over mu squared, plus coming from other fields. I will be interested only in the gravitational parts of the 0 to 2, where L is the ultraviolet cutoff. And we know that the ends in front of the divergent terms are always local. That's very important. While the effective action, after subtracting the divergent terms, can be non-local. That's a very fundamental thing. Okay, so we know that they are always local, and therefore they can be calculated. And in fact, beta 2 and beta 3 depend on the gauge choice, namely the offshore extension of the model, how we couple the fields to gravity. Beta 1 does not. This is the Gauss-Bonnet term, which is roughly the R mu euro sigma squared minus 4 R mu squared plus R squared, and this is Weil tensor squared. So there are two combinations, and this is R squared. So they are always local. We are interested only in before. That is correction to the cosmological constant. That is correction to masses. If we start from the conformally invariant theory, there are no corrections of that. So before is the divergent term that we are interested in. So now the link between gamma infinity and the conformal anomaly is roughly the following, namely that's the dependence on the scale after subtracting L squared and L to the fourth terms. That's the anomaly. That's the definition of the anomaly. And it is actually related. Since we will see later on, it has to satisfy the Versumino consistency condition that delta A of x sigma is the conformal factor in front of the method. So that should be satisfied. That comes from the fact that A of x should come from some effective action, from some derivative of the effective action. So this leaves only two possibilities, C squared and E4, and the CS and AS depend on the spin of the particle that we integrate over. So we will be interested from S from 0 up to 2. 0, 1 half, 1, 3 halves, and 2. And now, with contribution to this is excluded, because R squared does not satisfy this. Both E4 satisfies this, and C squared satisfies this. And box R can be dropped from the possible expression, because box R can be obtained from the derivative of R squared. So derivative of the local term. We are interested only in non-local terms of the effective action. Okay. Now to keep the link between gamma infinity and A, there were many different calculations of AS of these numbers. Many different calculations. That after some time, people agreed that C0, A0, C1 half, A1 half, and C1 and A1 are unique. Everybody agreed on these values, but there was disagreement, actually up to now, about C3 halves and A3 halves, and C2 and A2. So contributions from gravitinos and contributions from gravitons. There was a difference depending on the gauge choice, on the extension of gravity. So what we propose is that to keep the link between gamma infinity and A, we propose to impose the condition that the only admissible off-shell extension is the one where beta 3 is 0, namely when we calculate the infinity, this vanishes. Because then we have a direct relation between gamma infinity and anomaly. Anomaly precludes the presence of this term. And that makes the calculation of C3 half A3 half, C2 and A2 unique. And that will be the numbers that I will use. And this uniqueness is given by this table. So these numbers were all agreed upon a long time ago, while those two gave different results depending on the offshore extension. Now we claim that those are the correct ones. That requires an explanation. For spin 0 in 4 dimensions, we can either use a scalar particle or we can use an antisymmetric tensor. There's a duality between a scalar and an antisymmetric tensor. That doesn't change the CS, but AS comes from a topological term. So changing the boundary values from a scalar to antisymmetric tensor changes the value of the contribution. Now the question, so we claim, that will be argued in a minute, that only the theory where sum of those times the number of respective scalars, fermions, vectors, and so on, should be 0. So these numbers look very strange. So to find a theory where these sums are 0 separately, normally we expected that one would require very, very strange theory. It turns out not to be the case, that we already know theory that has both coefficients vanish. But why it should vanish? Now comes the argument. If we have the anomaly should arise from such a term. That's the energy momentum tensor, and we take the trace. Anomaly is the trace of the energy momentum tensor. So it should come from some action, and this action should be non-local. Because if something is local, we can add a counter term, and we can remove any such thing. So gamma anomaly should be non-local. For example, in equal to, we know the expression that was given by Polyakov, that the anomalous action is R1 over box R. That's the only action that one can get. That is no that gives rise to Liouville action and so on. And let's calculate from this. Let's calculate T mu mu. We know that T mu mu, as related to gamma infinity, has to be local. The only local expression in 2 dimensions is R of dimension 2. Is R, so the trace will be proportional to R. But let's ask about T mu mu. So this part without taking the trace, to see actually the non-locality of this action. So we calculate this. That is very easy. We see that we have a local term. This is non-local. This is non-local. But when we take the trace, all these terms vanish. And what remains is this. So that's, first of all, it is conserved. It has to be, because we started from the diffeomorphism invariant action. And moreover, the trace is proportional to a local thing, R, as it should. But we have non-local expressions here. Now we want to ask the question, how does such an action, or such a T mu nu, looks like in 4 dimensions? Not in 2, but in 4. The question is much more difficult and is not solved up to now. We don't have a full action that gives the anomaly, but we have parts of it. There are different versions. One of them is the so-called Rieger action, based on the inverse of Panay. So this is the analog of box plus 1 over 6 times R. So for when we have only 2 derivatives, that's the conformally invariant operator. In 4 dimensions we have this. There's a whole family of 3 boxes, 4 boxes, and so on. That's the first one, the Panay's operator, and inverse of that operator is part of the effective action. For the sake of the argument, we will use part of the effective action, namely something that box to minus 1 of this times box to minus 1 of R, and I will ask, what is it in the radiation era? So we start after the Planck time, let's say sometime after 1,000,000 times the Planck time. we go over, we are sure that there was a radiation era at that time, and we end up at 380,000 years, where the radiation era stops. And we want to calculate what is T00 coming from this anomalous action. So for the metric, we use the metric in conformal coordinates, where it takes conformal time. We know exactly the Green's function in these coordinates, because we want to translate it. We see that it goes along the light cone, the Green's function, and we use, for the radiation era, we use what is eta, the standard expression that is squared root of time. A of eta is proportional to eta. Those are very standard things. That corresponds to t to 1/2 in the cosmic time. This is roughly, we take the expression from the perturbations, usual perturbation in the radiation era, but main contribution comes from this. This which we use as part of it here. Yes. So we want to calculate this expression and take the time derivative of that. And it turns out that it can be done exactly from some eta0 corresponding to n star Planck length. We take this roughly, I don't know, 1 million or 1 billion, something that is very deep already in the radiation era. We don't want to go backwards until the Planck time. We want to be from the end of the radiation era to some time after the Planck era, not to have any problems with quantum gravity or whatever. It's purely classical consideration. And we plug it in, and it turns out that the result for T anomalous is roughly this. I neglect some aids or whatever. While the contribution from the Einstein-Hilbert action at that time is roughly 1 over L Planck squared times 1 over T rad, or T radiation squared. And we see that this contribution is much bigger than this contribution. So, even though normally we say that the Einstein-Hilbert action is the dominant one, because it starts from 1 over Planck length, the Planck length squared times r, so whatever we have as a correction, for example, r squared, normally is completely negligible. But since this is non-local and goes back to the early times when the curvatures were very, very high, it, in a sense, compensates for the fact that in front of it we don't have 1 over Planck length squared. So, if the T00 anomalous would be there, it would completely change observable gravity. We wouldn't have planetary motions, we wouldn't have gravitational waves, because the anomalous part of the action, this non-local action, would completely dominate gravity. So, our conclusion is that the conformal anomaly should vanish in any acceptable extension of the standard model. So now we ask, what are the theories, if there exist theories, that have vanishing conformal anomaly? So in which the particle content is such that sum over Cs times appropriate number of fields of a given spin S is 0, and sum over As, these coefficients in front of the C squared and in front of the Gauss-Bonnet, is whether such, and that was a very, very big surprise for us, that if we plugged in these three fields, namely n extended supergravities, they have very precise number of fields. There is one graviton, for example, for n equals 8, one graviton, 8 gravitinos that show that it is n equals 8, 28 vectors, 56 fermions, and 70 scalars. When we plug this times these strange numbers that we have here, it is 0. And the same concerns As. When we take the same numbers and we use these numbers, the sum is 0. So that was an absolute surprise for us that it is so, let's say, easy to satisfy these two. n equals 7 is the same as n equals 8, so we don't have to check it, because n equals 7 supergravity has the same number of fields as n equals 8, because we have to have CPT, so it's the number of fields is the same. So we have to check this. Then we check this, and it turns out that for AS, the same things happen, but n minus 3 scalars have to be replaced by n minus 3 antisymmetric tensors. So for n equals 8, we have to have 65 scalars and 5 antisymmetric tensors. Here we have to have 27 scalars and 3 antisymmetric tensors. So these cancellations are very, very strange for us. And we suspect that these cancellations for n greater than 5, greater than 4 supergravities are pointing to something very, very deep. We don't know what. But one should mention that also the work of Silverne, Kosover, Dixon, and so on, they show that for n greater or equal than 5, there are very special finiteness properties of these theories. They do not hold for n equals 4. They start from n equals 5. So maybe it's connected also to these extraordinary finiteness properties of these theories. Of course, we don't know yet. There's the problem there with 5 loops, but up to 4 loops, these theories are extraordinarily finite. They are much more finite than one would expect by writing the calculus. So maybe this thing, we don't know how, because we don't see anything. The one thing is in reverse order. If there was a conformal anomaly and we would add it to the action, we know that from 4 loops onwards we would have divergent curves. So the fact that these do not have conformal anomaly, whether it is related to the fact that there is no divergence, we don't know. Okay, two remarks about this. In gauge n equals 8 supergravity, that is an old paper by Nick Warner and Herman Nicolai, there exists a vacuum with SU3 cross U1 group, and the matter sector has quarks and leptons with proper SU3 assignments. That was already noticed by Murray Delmar a long time ago. It turned out later on that quarks and leptons have proper charges. So, for example, the up quark has plus 2/3, down quark has minus 1/3, neutrino has 0, and so on. So there was a problem with this assignment for a long time. And one thing that is very important is n equals 8 supergravity, when we break completely supersymmetry, has 48 fermions. Because this has 56 fermions, but 8 fermions are eaten by super Higgs mechanism. If we have n equals 8 broken to n equals 0. So what remains is exactly 48 massless fermions. That is exactly the number of the standard model with 3 generations. Maybe that's some kind related to the fact that we have 3 generations. The cosmological constant problem, unfortunately, remains. Another thing is the conformal standard model. We use conformal symmetry to replace softly broken supersymmetry, but softly broken conformal symmetry. And we have some requirements, renormalizable, a seesaw mechanism for neutrinos to make them like B minus L broken, only spontaneously, model viable to Planck, mass, no low energy SUSY, no guts, nothing like this, stable vacuum. I recall that the standard model has unstable vacuum. There should be a candidate for cold dark matter, and observed value to photon. So all the requirements that we should normally put. And such a theory was constructed 10 years ago, roughly. We propose to call it the conformal standard model, and it is much simpler than MSSM. It has only several new parameters. MSSM has 616 new parameters. The only new particles are 6 complex scalars, and it's enough to satisfy all the requirements that we have. New scalars are necessary in this theory because of B minus L symmetry and seesaw. 125 GeV Higgs, discovered several years ago, is not a pure doublet, as normally in the standard model, but a mixture of the standard model Higgs with one of these scalars. So that's one. The prediction of the model is that an orthogonal combination should be observed as a new heavy scalar by LHC with mass of several hundred GeV up to 1 eV, let's say, or 1.5. So that's our prediction with very, very precisely known properties, except its mass. So if someone gives us the mass of this particle, in our model it's exactly this. So, and it is very peculiar. It is not, these properties are different from anything else that we know. And phases of these scalars are naturally very large, below the masses of neutrinos, and extremely weakly coupled. The decay of two photons is much longer than the age of the universe. And it's very natural for reasons that I don't have time to explain. So summary. All the incredible achievements of Newton, Einstein, Lemaitre, and so on would be ruined if there was non-vanishing conformal anomaly. The requirement of the vanishing of both conformal and anomaly coefficients is an extremely strong requirement and singles out any extended supergravities with n greater than 5. There has been a paper on that recently. N equals 8 gauge supergravity has very special properties, possibly explaining 3 generations of quarks and leptons in the standard models. The cosmological constant problem is not solved by this. Conformal standard model that I have briefly described is a viable simple proposal of extending the standard model with a new scalar, mixing with the Higgs as a testable prediction at the LHC, and we predict also very light, extremely weakly bound particles, candidates for cold. Thank you.